And welcome back. As we continue our cosmic journey through the stars, we are now going to go ahead and start taking a stellar census of the kind of stars that we might see around us. So the first thing you might notice if you were to look at our night sky is a variety of stars. This image in particular shows a part of a cluster of stars in the small Magellanic Cloud located about 200,000 light years away and is about 65 light years across. Now the stars in this cluster are all about the same distance from us. And the differences we see in apparent brightness correspond therefore in distances in luminosity. Differences in temperature account for the differences we see here in color. Now the various colors and luminosities of these stars provide us clues about their life stories. Now the first thing you have to understand is that small stars are pretty beautiful and actually are much more common. In fact, if we look at this table here below, we see an estimate of the number of stars each spectral type in our own local neighborhood for about within 21 light years. So we have spectral type A, F, G, K, M, and we have white dwarfs and brown dwarfs. And you can see the number of stars that we have here, 2, 1, 7, 17, 94, 8, and 33. You'll see that there are actually very many more low luminosity and hence low mass stars than we have of high luminosity ones. In fact, the M spectral type seems to be the heaviest category, and even though we see brown dwarfs are the next highest, brown dwarfs are very hard to detect, so this number could actually be even higher. Now, only 3 stars in our local neighborhood are significantly more luminous and massive than that of the Sun, so that would be the A and F stars. Now, the Sun is more massive than most stars in our vicinity. It is very likely that there are more faint objects remaining to be discovered. As I already mentioned, brown dwarfs are very hard to detect, and so that number that is in that table there could be very inaccurate because we could have more brown dwarfs out there. Now, along with the L and T brown dwarfs already observed in our neighborhood, astronomers expect to find perhaps hundreds of additional T dwarfs and Y dwarfs, which of course could skew that number even further to that kind of low luminosity side of the scale. Now, many of these are likely to be even cooler than the coolest currently known T dwarf. Now, the reason the lowest mass dwarfs are so hard to find is that they put out very little. Tens of thousands of million times less light than our sun. And you got to remember, there's also a distance between us and those brown dwarfs, which means that that light is going to register much less in its apparent brightness. Only recently have we had the technology to progress to the point that we can really detect these dim, cool objects. Now, another thing to keep in mind is that just because a star appears bright does not necessarily mean that it is close. Now, a clue that we are missing something in our stellar census, such as all those brown dwarfs, comes to the fact that only 6 of the 20 stars that appear brightest in our night sky are found within 26 light years of the Sun. This would be Sirius, Vega, Altair, Alpha Centauri, Fomalhaut, and Procyon. So you might be wondering, why are we missing most of the brightest stars when we can take the census of our local neighborhood? Like, why is there only 6 of these 20? Well, the first thing you have to keep in mind is that the answer to this question is that stars that appear to be the brightest are not necessarily the ones closest to us. Again, only 6 of those 20 stars are within that distance. Now, the brightest stars look the way they do because they emit so much energy that they do not have to be nearby to look so brilliant. In fact, the most distance of these stars is more than 1,000 light years from us. And it turns out that most of the stars visible without a telescope are actually hundreds of light years away and many times more luminous than that of our own sun. Among the 9,000 stars visible to the unaided eye, only about 50 are intrinsically fainter than that of our sun. So let's consider for a moment the most luminous stars, those 100 or more times as luminous as the sun. And though all such stars are pretty rare, they are visible to the unaided eye even when hundreds of thousands of light years away. A star with luminosity 10,000 times greater than that of the sun can be seen without a telescope out to 5,000 light years. And you might think, okay, 5,000 light years, that much, but that can't be too much, right? It's only 5,000. It could be like 50. Well, just remember that the volume of space included within 5,000 light years is enormous, because that would be the amount of time it would take light to travel 5,000 years. And that's a long time because light moves pretty quickly. And even though highly luminous stars are intrinsically rare, many of them are readily visible to our unaided eye. The contrast between these two sample stars, those that are close to us and those that can be seen with the unaided eye, those very bright stars in our sky, is an example of what we call selection effect. When a population of objects includes a great variety of different types, we have to be careful what conclusion we draw from an examination of any subgroup. It requires us to have much more effort to assemble a complete data set for the nearest stars, since most are so faint that they can be observed only with a telescope. However, it is by doing so that astronomers can know about the properties of most of these stars, which tend to be smaller and fainter than that of our own sun.